So, welcome. Good evening, everyone. Super excited to have you all tuning in for the Chegg Gen Chem Office Hour. My name is Dr. Janita, or you can call me Dr. J. And I am super excited to be leading tonight's office hour where we're going to talk all things general chemistry. A little bit about me for those that might be new to this space. I have my PhD in analytical chemistry. I've spent years teaching. More than 2 decades actually teaching this topic, and also run a nonprofit that focuses on introducing K through 12 students to STEM, or science, technology, engineering, and math, and add the A in there, and we turn it to STEAM, which means we also incorporate a little art. But I launched this particular platform, Gen Chem with Dr. J, to help people as they're navigating their own personal Gen Chem journeys. I'm super excited to partner with Chegg to host tonight's office hours. So for those of you that might be new to Chegg, they are here to make your academic journey a bit smoother. They have a ton of resources to help get you through school, like online study help, expert Q&A with step-by-step solutions, writing support, and a whole bunch more. If you click that QR code in the top corner, you can find more about the courses that they host and see all the various resources that are available for you. So for those of you that are here for the first time at one of these live office hours, welcome. And for those of you that have been here before, welcome back. Super excited to hear all of your questions as we go through today's session. So think of this as a virtual office hour. I want to hear from you. So if you put in the chat topics or questions that you're struggling with, we'll try to get through as many of those as we can tonight. Again, this is going to be as interactive as possible. Make sure that you have a piece of paper nearby so you can practice the problems with me as we're going through. And also, I always like to make sure that students have set themselves up for success as we are working this office hour. So make sure you have your calculator nearby. I have my calculator here. Doesn't have to be a fancy calculator. You just need one that can do scientific notation and exponents. And so I have my calculator nearby. You also want to have a periodic table. Again, the periodic table has so much information that we use as we're solving different problems. And it's a good tool to have nearby. Thinking about your calculators, it's also great to follow along as I'm doing some of our problems so that if you're not getting the answer correctly as we're practicing together, you can let me know in the chat and so we can try to figure out what's going on, okay? So again, put your questions in the chat. I'll be sure to get through as many of them as possible. I did want to start today with a couple of questions that I had that came through on my platform earlier this week, and that is about balancing equations. How do we balance equations? You know, we've been on a journey over the last couple of weeks as we've been hosting these office hours. We learned about what are atoms, subatomic particles. We talked a little bit about moles and mole island and how do we convert from all of these different units like grams or atoms to moles. And where we're going is what my chemistry teacher used to call the big S in the sky, which is all about stoichiometry. So we're going to get into some stoichiometry problems today, but the first thing that we're going to have to know how to do is how do we balance our equations? And so again, you can follow along with me. We will get right into, these are some of the problems we've done before. But we're going to get into how do we balance equations. And so when you're doing a chemistry problem, oftentimes you're going to see a chemistry equation or a formula that's provided for you that's telling you what are we reacting and what are we producing. Okay. And so when we're doing this, we want to make sure that we balance our equation, which means that we have the same number of atoms that we start with in the reactants and on the product side, okay? And so when you look at any type of chemical equation, anything that's before the arrow, like such, these are called your reactants, okay? And think of your reactants kind of like if you're in the kitchen cooking, they're your ingredients. They're the things that you're starting with. So like, let's say you're making pancakes and you want to have some pancake mix and water and maybe eggs. Those are your reactants. Those are going to be the things that we're going to be mixing together and making a chemical change occur. Now, very similar to like when you're cooking, when these things undergo a chemical reaction, something new is going to be formed. Just like when we're making our pancakes, when I mix my eggs, my flour, my water, I make my pancakes. That is my new thing. And so the thing that's produced, which you see after the arrow, those are what are called your products. Okay. And so for any chemical reaction, as you can see on the 4 examples here, you're going to have a set of reactants, that's your starting material, and then a set of products. Now, what you should notice in the examples that I'm showing you here on the screen is that sometimes you can have 2 reactants and make 1 product, like in number 3, or you could have 2 reactants and make 2 products, or you could have 1 reactant and make multiple products. Okay. And so there are a lot of different ways or flavors that these reactions can show up. But regardless of how they're structured, whether it's 2 reactants, 2 products, or 1 reactant, 2 products, etc., our first step in any of these problems when we see a chemical reaction on a test or a homework problem is we got to make sure it's balanced. And so really this is just like a checking system. However many I see on the left side of the arrow, I need to account for that same amount on the right side of the arrow. Okay. Now, when we're balancing the equation, we're only going to be focusing on putting numbers in these positions that come before an element or a compound that might be present. Those positions are what are called your coefficients. Okay, so coefficients. So sometimes you're going to be asked to find what are the coefficients of an equation. Okay. And so there's a lot of ways you can do this, but what I like to do is I like to actually go to the arrow of any chemical reaction and I list the elements that I see present. So for the first one, I would say magnesium, I see oxygen, and I see carbon. Okay. And then I'm going to count how many of those atoms, how many of those elements do I see on each side. So on the left-hand side, in my reactants, I see I have 1 magnesium. So I just put it there. I also have 1 oxygen. And then I see I have 1 carbon, right? So I'm just counting how many atoms that I have. Now on the product side, I have, again, 1 carbon. But now I have this subscript here behind the oxygen. So that's telling me that I have two oxygens, okay? And then for magnesium, I only have still 1 present. Now, this method I love because, again, I've told y'all before, I'm a visual learner. I'm a visual person. And so now I can easily see what is not balanced, right? And if we look at this, you can see that oxygen is the thing that I should probably focus on first to try to get it balanced. And so when we're balancing, what we are doing is we're going to be putting whole numbers into these coefficient positions to try to balance things out. I can't just come and put like a 2 there and say, oh, MgO2, because that would be changing the reactant that I have present. So instead, I have to put a number, a whole number in that coefficient position. And whatever number I put there at the beginning, it basically gets multiplied by however many atoms I see present in the compound. So if I put a 2 in front of the oxygen, I now, instead of having 1 oxygen, because I'm now having 2 of these compounds involved in the reaction, I now have 2 oxygens. But you should be like, whoa, 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 Dr. J, by you doing that, what about magnesium? Because putting that 2 in that coefficient position also changes how much magnesium we have. And so that would now mean we have 2 magnesiums. And so now we got to go to the product side and alter there. Again, we don't put a 2 here, not in the subscript position, only in that coefficient position. And again, we're looking for a common multiple on both sides. So to balance that out, we would need to put a number 2. Okay. Did you all get that one right? All right. Awesome. Oh, and see, DC, you're asking to balance some equations. So I got you. We're great minds think alike. All right. So let's try another problem. Okay. Because that one was a pretty easy one to get us warmed up for this balancing equation idea. Okay. And so look at the second problem. Again, I see that there's no numbers present in that coefficient position. And so I'm going to now put my carbon, my hydrogen, and my oxygen below. And I'm going to actually count how many do I have. So for carbon, I see that I have 2 carbons to start. I have 6 hydrogens, and I have 2 oxygens. Okay. Well, let's switch to the other side, the product side. Here I have 1 carbon. My hydrogens, I have 2, again, counting that subscript. Now, oxygen, note what do you notice about oxygen in this case? Well, what you should be saying is that there's oxygen in 2 places. I have 2 plus 1 over here. So we actually have 2 plus 1, or you could just say you have 3 there. Okay, so that's the total we're trying to get to, right? So we want to make sure that we remember that oxygen is in 2 different places. Okay, so now this is where we have to figure out, well, how are we going to try to balance this out? What are we going to do? Okay, so you might say, let's try starting with the carbon. I see it listed first, and we can do that. All right, so with the carbon, I see I have 2 of them on the reactant side. That means I likely should put a 2 in front of the carbon. Okay, so that changes how many carbons I have, but it also changes my oxygen. I now have 2 times 2 plus 1 more. I now have 5 oxygens and haven't changed my hydrogen just yet. Okay, all right. And so now let's think about our hydrogen. Well, with the hydrogen, I have 6 on my reactant side. And if we're trying to find a common multiple between them, we would probably say, well, if I have starting with 2, my common multiple, if I put a 3 there, well, 3 is going to allow me to now get 6. 3 times 2 gets me 6. But now with my oxygen, I now have 4, 2 plus 2 over here, plus 3 more. Okay, so that gives me 7. And so remember, we have to put whole numbers here. And so this is actually kind of a common type of problem. This is what's known as a combustion problem, where you have this hydrocarbon, this carbon and hydrogen reactant reacting with oxygen. So when we see this pattern where we have oxygen and it's splitting into 2 different compounds, into carbon dioxide and water, typically, if you're trying to balance out your oxygens, if you end up with an odd number in this H2O portion, no matter what you do, an odd number of oxygens being added to an even number is going to give us an odd number. And so there's not a whole number that we would be able to put in this position that would be able to balance that out. So what we're going to want to do is we want to get rid of that odd number. And the simplest way to do that is to simply double the number that we originally put there. Now that double is going to help us because, one, it's going to allow us to easily rebalance out our hydrogen, but it's going to get rid of that odd number that was there. So instead of a 3 there, I'm going to put a 6. Okay, and we're going to see how this is going to change some things. So the big thing to remember also with balancing equations, once you put a number down, it doesn't mean it's stuck there. Okay, you can erase it and keep moving. All right, so now by me putting that 6 there, hydrogens, I now have 12. Okay, and on this side, my oxygens, I now have 6 from this one, plus 2 times 2, that gives me 4. So 6 plus 2 gives me 6 plus 4 gives me 10. Okay. But now we've changed our hydrogen. So we actually got to go back over here and change our hydrogen on the other side too, because now we have 12 on the product. And this is why I love this method, because I can see exactly all my work. That means I need a 2 here. So a 2 in front of the C2H6. So that now gives me 6 times 2 gives me 12. But wait, that's changed my carbon too. So carbon, I now have 2 times 2, which gives me 4. And so that means we're now going to go back to that original 2 that we put down. And guess what? It gets doubled now, just like that 3 did. And so now we have 2 times 2 on the reactant side. That gives me 4. by putting a 4 there. That now gives me 4, so that's checking out. And so now the only thing we got left is the oxygen. So with the oxygen, I have a total of 10 now. So the number I need to put in front would be, well, if I have 2 of them, what would I need to multiply by? That would be the number 5, okay? And so now, using this method, this kind of tracking method, you can see that everything is all balanced and we would be good to go, okay? Hopefully that helped. All right, awesome. Sounds great. All right, so I'm going to move on because I'm seeing a couple of questions from a few people that I think sounds like there's some interest in. So I'm going to move on. You can screenshot these practice problems and let me know if you're able to balance them in the chat later on. Okay, but let's try getting to some of the questions that I see in the chat. So I see both DC and Lizette. So Lizette on TikTok, DC on YouTube are asking about molarity. Can we talk about molarity? Okay. And so, yeah, we can do that. And I love talking about molarity because, again, I have a nice little visual hack, hopefully that will help you out as you think about those calculations. So molarity is the way that we describe the concentration of a solution. And so when we're mixing things in the lab, we often have a solute, which is the thing that's getting dissolved. So like think about it if you're at your house and maybe you put some sugar into a solvent like water. And the combination of those two make a solution, okay? Now I can put a lot of that sugar in there or a small amount of that sugar. Well, the molarity is going to tell us about the strength, how strong, how concentrated is the solution that we've created, okay? And as the name implies, molarity is going to involve the mole, okay? We learned about moles before. The term mole is a counting system, right? It's how we count very small things. But in this context, molarity is going to be looking at the relationship of the moles of the solute, okay? So in that example I just gave of the sugar that I put in there, compared to the volume of the solution, okay? And so molarity equals the moles of your solute divided by the volume, and this is of your solution. Now, importantly, your volume has to be in liters, okay, for you to get your molarity. And you end up with the symbol of capital M for molarity, okay? Now, this is a 3-variable equation that you can use often. If you tuned in early on, I think like week 1 that I was doing these office hours, I showed you a trick that you can do with 3-variable equations, and that is this triangle trick, okay? And so if you're ever struggling with solving for any of the variables in molarity, what you're going to do is draw a triangle and make like a T on that triangle. Now, in the bottom left corner, you're going to put capital M for molarity. On the top, you're going to write moles. And on the bottom, put volume, okay? Now, this T is telling you what kind of operation we're doing, right? The top of the T in the middle, this represents a division symbol. And this part here, the cross section here, represents a multiplication symbol, okay? And so if I'm solving for one of these variables, right, if I have a problem that tells me about the moles and the volume and I want to solve for molarity, all you're going to do is you cover up, I'm drawing on it, but you can put your hand over it, cover up the variable, and what's left is the formula. So if I cover that up, what's left is moles divided by volume. Well, let's say, what if I wanted to solve for the moles? We'll cover it up, and what you're left with is moles would equal molarity times volume. Or if you wanted to solve for the volume, cover it up, and then you're left with moles divided by molarity, okay? And so I show that little visual trick because, again, what you can do is you can draw your triangle right on your test. As soon as you get your test, draw it. That way, when you get to a problem, you're actually able to use it. Okay. So let's do a problem here. How would we solve this problem? So sometimes you'll be given information like this. What is the molarity of a solution of a 0.57, actually, sorry, 575 milliliter solution with 0.385 grams of, let's say, sodium chloride. Okay. All right. So this is what a typical problem might look like. So what is the molarity of a 575 milliliter solution with 0.385 grams of sodium chloride? Okay. And so we got some information here, and we're going to figure out how do we plug this into this equation. And so I see that I'm given a volume, right? So this is my volume. And then I'm also given this mass information, okay? And so the mass is great, but I do know that I'm going to have to do a little bit of work to be able to use this formula, because this formula needs moles, not mass, okay? And so what we'll have to do is convert our mass to moles first, and then we would be able to use this equation appropriately, okay? You should also be saying, well, wait, Dr. J, what about that volume? Yeah, we're going to have to convert that too, but we'll get to that in a second, okay? And so with our mass, let's go ahead and convert that first. And so we have 0.385 grams of sodium chloride, and we want to get it to moles. All right. And so remember, when we're going from grams to moles, we're going to be using our molar mass, which we can pull from our periodic tables. You would have to find the mass of sodium, which is 22.9, and the mass of chlorine, which is 35.453, and add those together to get the molar mass. So that's 22.99 plus 35.453. And that gives us 58.443. Now, we're going to use that equals 58.443. So we're going to use that in this equation here. So I'm going to put grams on the bottom and moles on the top. And I'm going to plug in that molar mass of 58.443 on the bottom is to 1 mole. And that gives me 0.385 divided by, well, times 1, but then divided by 58.443. And that gives us 0.0065876615. And if this was the end of the problem, we would be stopping there for sig figs because we only need 3 coming through. All right, and that's moles. Now, for the molarity part, well, molarity, remember, is going to end up being moles divided by our volume. So I'm going to take that mole amount that I got, that 0.0065876615. You do want to carry all of the numbers through. Don't round too early. All right, so that many moles divided by, now our volume, remember, has to be in liters. And so we have 575 milliliters. You can do the unit conversion step, set up the milliliters to liters conversion using the 1 times 10 to the third value, or you could just move your decimal point 3 times. So take the decimal point, move it 3 times. And so that would give me 0.575 liters. Okay. So now I can take those numbers and divide. So take your moles divided by your 0.575, And that now gives me 0.01145672, capital M for molarity. And with proper sig figs, we would have 3 sig figs. And so we would be stopping here. And our final answer would be 0.0115 molarity. Okay. All right. And I'm seeing David on TikTok, milliliters to liters. Perfect. So, yep, you were already thinking about that. And again, mass to moles is necessary there. And isn't there an easier way to do these? Well, Perla, it kind of depends, right? It depends on what information is given. Sometimes you're given moles from the beginning and you don't have to do that extra step of getting to moles first. So it really depends on the question that you're given, on how easy or straightforward it would be. But the rule of thumb is typically if you don't have moles given to you in the problem, get to moles in whatever way you can, and then continue on from there. Okay. All right. All right, so let me get through a couple more questions here. So I see a question from Into You Keys 1 on TikTok. Could you go over nomenclature? Okay. And so, yeah, we can talk a little bit about nomenclature. And again, keep putting your questions in the chat. We'll get to as many problems as possible. So nomenclature. So nomenclature is how do we name things, right? Nomenclature. Okay. And so when we're naming compounds in general chemistry, there are 2 primary naming formats that we're going to be naming, or how we're going to be naming things. Okay. One format is for molecular compounds, and one format is for ionic compounds. Okay. And ionic compounds actually have kind of like a subcategory under there. All right. So first things first, you have to know what's a molecular compound, what's an ionic compound. Okay. Molecular compounds are compounds that typically don't have a metal present. Okay. They typically contain your nonmetals and nonmetals, or nonmetals and semimetals. Okay. Whereas ionic compounds, they typically do have a metal present. They come together by forming ions. So you have a cation and an anion that are attracted to one another. Whereas a molecular compound, you have these individual discrete molecules that are sharing electrons, not transferring electrons. Covalent. So they do covalent bonding. Ionic compounds do ionic bonding. But when we're naming them, we have different naming formats. And so for molecular compounds, when we're naming them, there's a couple positions that we're going to be thinking about. Okay. So the first thing we do is we use a prefix to describe how many of the first element are present. All right. So this is for binary molecular compounds. So when you have 2 elements present. So you use a prefix to describe how many of the first element that's present. You then list the first element's name. You then have another prefix that will describe how many of the second element you have. And then you would list the second element plus the IDE ending, IDE, okay? Now, very important in this position here, we can never use the mono prefix, okay? So like, for instance, when we see like this compound, CO2, well, CO2, there's 2 nonmetals, right? Remember your metals, if you look at your periodic table, there's a little step here. These are metals, nonmetals, semimetals. So we have 2 nonmetals, carbon and oxygen. So if I follow this format, the prefixes that we're working from, there's mono for 1, di for 2, tri, tetra, penta, and so forth. We only see 1 carbon here. However, we're not going to say monocarbon. We never use the mono prefix in this first position. So if we name this, we would just say carbon. Then we have a prefix that describes the second element. Well, there's 2 oxygens present. And so we would say di, and then the second element plus ide ending. So that's oxide. So that would be carbon dioxide. Okay. So we use that format whenever we're dealing with molecular compounds, no metal present, things that do covalent bonding, meaning they're sharing their electrons. Now, ionic compounds, we don't use those prefixes, okay? Because an ionic compound in reality is really multiple cations and anions that are present. And what we report out is the simplest whole number ratio that exists between those ions, okay? So it's not these individual units. We're really referencing what's the ratio between these two. And so when we're naming them, we have to also be mindful with the cation or the metal that's present. Is it a metal that has a fixed charge? Meaning that anytime you encounter this element, it's always going to have the same charge, okay? So your fixed metals, or cations, actually is the better word to say, your fixed cations include elements in group 1, group 2, and then there's a few other random elements that are spread throughout your transition series. And then one that's in row or column 3. So we have group 1, group 2, aluminum, which always is +3, silver, which is +1, zinc, which is +2. Okay. All right. And so when we're doing this, when we're naming this, if they're a fixed element, the fixed elements are always going to be, when we name them, we don't have to state their charge, right? And so for your fixed elements, when that cation's present, you're just going to say the cation name. All right. Then you would say the anion plus the IDE ending. Okay, so for instance, if we had AlCl3, we would just say aluminum, which is the cation, aluminum, then chloride. We wouldn't say aluminum trichloride because we don't use those prefixes here, okay? For your any other metal outside of those that we've listed, right? We're going to now be saying the charge of the metal. Okay, so you'd have your cation, you'd still have your anion plus the IDE ending. But now in parentheses, you're going to be putting the charge of the cation. Okay. So for instance, if we had something like FeCl3, okay, so iron is not one of those fixed elements. And so we actually need to figure out its charge first before we can name it. And we can do that by knowing that the cations and anions in these neutral compounds have to balance each other out. Chlorine, which is a group 7 halogen, would take on a -1 charge, all right, because it has that 7 valence electrons. It would prefer to take on 1 more electron, so its preferred charge is -1. And so if there's -1, but we have 3 of them, that means this iron is +3, right, by charge balancing those. So when we name this, this would end up being iron 3 chloride. Okay. So I hope that helps into you keys on TikTok with your nomenclature. Again, you're looking at what kind of compound are you naming? And then if it's molecular, you're using those prefixes. If it's not molecular, you're going to be using those, the cation and anion format, and then indicating the charge if it is present. Okay. Awesome. All right. All right. So I'm seeing a couple of other questions that seem to have some similarities to them with them. Oh, let's go to, and I had a couple more molarity problems. So I see one that's talking about, I see two questions, both from TikTok. One is from nonetheless, from TikTok. Can you explain orbital diagrams? And I see someone else also asking, user 137438283, asking, can you explain the difference between electron configuration and orbital diagrams? So yes, we can do both of those. Okay. So electron configuration and orbital diagrams, they're kind of connected to one another. They're basically a way for us to tell where are the electrons that are found in these atoms, where are they located in the atom, essentially. So when we're doing electron configuration and orbital diagrams, we're accounting for every electron that's present in an atom. And we do it in a way that allows us to acknowledge what energy level is the electron in. I kind of like to think of it like almost like a map of a neighborhood, right? So the energy level is kind of telling us like what street are you on. So if you think about an atom, right, that's the nucleus, and then there's all these energy levels that surround the nucleus, right? And the further away you get from the nucleus, the more and more energy there is. Okay. So think about each one of those rings that's around the nucleus, that represents an energy level. And so when we're doing the electron configuration and the orbital diagrams, we're saying, well, which energy level are you on, right? Are you on energy level 1, energy level 2, 3, 4, so forth, okay? Then we also describe, well, what kind of orbital is the electron housed in? Think of the orbital kind of like a house, right? So we have streets and we have houses. So there's a couple of different types of houses. There are s orbitals, which are smaller orbitals. They're more spherical shaped. There are p orbitals that are like two balloons. There are d orbitals. They are like four balloons. And then there are f orbitals, which are like eight balloons. And so again, if a house example, it's like a studio apartment, a townhouse, a single family home, and a mansion, right? So the f orbitals are huge. And each house, each orbital can hold different number of electrons, okay? And so your s orbitals, they can hold up to 2 electrons. Kind of think of it like 2 people in the house. Your p orbitals can hold up to 6 in there. Your d's can hold up to 10, and your f's can hold up to 14, okay? And so when you're doing electron configuration, it's also good. I showed you all a trick last week of how you can set up your periodic table. I'll put it up here actually. How you can set up your periodic table to help you when you're doing these electron configurations or your orbital diagrams, okay? And so if you look at your periodic table, the periodic table actually tells you just so much information, but it actually is structured in a way that's going to help us to do these electron configurations a lot easier. So the trick that I showed you all last time was that to put the number 1 over here in the top corner by the hydrogen, put the number 2 by the boron in the second set of the main group elements, put the number 3 by scandium, and put the number 4 by cerium, or you might see lanthanum at the beginning of that lanthanide series, okay? So those numbers are telling us what energy level we're dealing with in that subshell, okay? Also put the letter S here, which represents where our s orbitals are. Put the letter P on the second set of your main groups. Put the letter D in the transition elements, and then put the letter F down here at the bottom. Now, the brilliance behind the periodic table, if you count the columns that are there, like look at where the s orbitals are located, you should see 2 columns. Well, look how that ties to the fact that there's a maximum of 2 electrons present in the s orbitals. Look at the p's. Count those columns. There's 6 of them there. And again, that's the maximum that we can have. Look at your Ds. You should see 10 columns. And then your Fs technically have 14 columns. If you have a periodic table where you see LA and AC pulled out here, if you see LA and AC here, sorry, my A is a little wonky there. Really, the LA and AC actually are here. All right. But they're just sometimes periodic tables pull it down here because that's what they're named after. But I digress. So when we're doing the electron configurations, we're going to be accounting for every energy level, every subshell, every orbital that we're passing through, and then how many electrons are present. So it's kind of like a game, a typewriter that you have to act like to determine it. So let's pick an element. Let's do something like selenium. All right, so find selenium on your periodic tables. And once you find it, we're going to start from the beginning and do the electron configuration first, and then we'll convert that to an orbital diagram. Okay. And so starting at the beginning of where hydrogen is, this is why I put that 1 there, because that 1 tells me what number I'm starting on. So we're going to do, what did I say? Selenium. Okay. So this is the electron configuration. So we're going to start off with 1s. We're in the s subshell. And I'm going to count the columns that I got to pass. Again, for this purpose, helium is technically part of the s orbital, s subshell, excuse me. So I'm going through 2 electrons. So I put that 2 in the top corner as a superscript. Then once I'm past helium, act like a typewriter and go to the next row or the next period. Well, if I started on 1 at the beginning, I'm now jumping down to the number 2. So I'm at 2 and I'm going through that S subshell. So I would say 2S, count your columns, 2S2. Okay. Now we're jumping across to where boron is. Okay. So as we're doing this, we're going straight across to where boron is. Now remember, we put the number 2 there as well. And that tells us where our P subshell enters. So we would say 2P. Count your columns. How many we got to pass? Well, we got to get through all of those 6 to get to neon. So 2p6. Now we wrap around, act like a typewriter. So I was here at neon. I'm coming down here now to where sodium is. So if I started at 1, that was 1, 2. This is now the 3rd energy level. So we'll say 3s, get past magnesium, 3s2. Jump across again, we're by aluminum. Well, if I was at 2p6, the next row would be 3p. 3p, and then we would say 6 because we're getting through argon. Okay, now we wrap back around. You should be at potassium. Okay. Again, if I started at 1, if I'm 4 rows down, I would now be at 4s, and then the number 2 because I'm going through calcium. Now, when we get to the transition elements, this is where it gets a little fun because there's so much energy that's in that D subshell. Think about energy kind of like money. There's so much money, right? They're actually able to penetrate, get into that higher energy level, if you will, right? So when we're filling them, we're going to fill our D orbitals. They're technically in a lower energy level, but because of the amount of energy that they have with all those electrons, they get filled after our 4s orbital. So that's why I put that 3 there to remind me that I'm actually starting on the 3 energy level, D, and then count your columns to get to zinc, and that would be 3D10. And then last but not least, as I get to where selenium is, I am now back at the 4 energy level for P. So 4P, and then we count to what I need to get to selenium, which would be 1, 2, 3, 4, 4P4. Okay. So this is what's called your electron configuration. Now your orbital diagram uses the same information, but now we're going to be showing our electrons and showing which direction are they spinning. Are they spinning upwards or downwards? Okay. For your orbital diagram, you have to know how many of each subshell or how many of each orbital exist in that subshell, okay? Your S's, there's only one type of S orbital that exists. And so anytime you're saying an S, you'll just show one line, which represents the one type of S that exists, okay? When you're doing P's, excuse me, when you're doing P's, there are three types of p orbitals that exist. And so we would draw them with three lines, and that's where we're going to be putting our electrons. For your D's, there are 5 different types of D's. You can look up the pictures of these. Basically, they're in different orientations. Some of them take up more space. And then for your F's, there are 7 different types of F orbitals. Okay. If you ever forget how many of each orbital exist in that subshell, take the number of columns that are there in our labeled diagram, divide by 2, and that tells you how many you should be putting. Okay. So we're going to take the same information that we have from our electron configuration to get our orbital diagram. And so now I would say 1s, and I would draw one line above it. And now I'm going to take those 2 electrons that I said are there, and I'm going to put them into my orbitals. Now, there's a lot of rules that help us to understand electron configuration and orbital diagrams. One important rule is Hund's rule. So Hund's rule talks about how we're distributing our electrons, but also how many electrons overall that each orbital can hold. And so when we're putting our electrons in, we're going to be putting 1 electron going upwards as if it's spinning upwards, and then 1 electron going downwards. So basically it's spinning in the opposite rotation. Okay. And so you'll have 1 spinning this way, 1 spinning that way. Okay. For your 2s, we would do the same thing. So we'd say 2s, we would do a line, and we would go 1 up, 1 down. Okay, so again, sometimes it's helpful to do the electron configuration first if you have to do the orbital diagram as well. Now for 2p6, I'm going to show 2p, but this time I'm going to have 3 lines, 3 orbitals that I'm filling. And so now when I'm filling these, it's good to get in the habit of putting 1 electron in each orbital first. Again, this is Hund's rule, before you come back and make a pair. And so I'm going to take my 6 and I'm going to go up, 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 and then down, down, down. Okay. So get in that habit, because that's going to be really important, especially when we don't have a full shell. We're going to get to 3s. Again, one line for the orbital. Put my electrons in, 1 up, 1 down. All right. 3p. Again, p. I have 3 orbitals that I'm filling, and I'm going to go up, 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 down, down, down. Okay, we're almost done. 4s, we have 2 electrons, go up, go down. Okay, we still have our 3d. Okay, I'm going to clear some space over here. So for our 3D, now remember we have five different Ds that we can be distributing our electrons to. Again, I'm going to go up, up, up. So up, 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 and then down, 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 down. Then last but not least, we have 4p. There will be 3 orbitals. Now, this is where it's going to be really important. I'm not going to do this. Okay, that would be incorrect if you do it like that. You have to give 1 electron to each orbital first within that subshell before you come back and make a pair. I don't like the way that looks. Let's draw that a little better. There you go. All right. And so that would be your proper orbital diagram for selenium. Okay. Hopefully that helped. Def nonetheless, and user 137-43823 on TikTok to understand the difference. Okay. Isa, I'm glad I was able to help you out on TikTok with some nomenclature as well. Awesome. All right. All right. So I see a couple more questions that are coming through. And oh, Deborah, I'm so glad that this is exactly what you're learning. I'm glad that I was able to help. Hopefully that explained it a little bit easier for you as you have been working through it. So I see a question, Deborah. You asked about polyatomics. Can I talk about polyatomics? Sure. Polyatomics actually fit in really well with the conversation we just had around the nomenclature part. Okay. Let me get a clear board here. So polyatomic ions. Okay. Polyatomic ions are ions that are, there are a group of atoms that are together that have a charge. So if we break that word, poly means many, atoms from atomic, ions with the charge. Now, your professor likely gave you a chart of several to memorize, and there's a lot of them. There's like nitrate, nitrite, sulfate, sulfite, acetate, all types of them. Okay. And so I first recommend that you memorize those. When I was learning these many, many moons ago, I put on the front of my card the name. So I would write like nitrate. So nitrate is like NO3. I'm often going to bring nitrate up at some point whenever I talk about polyatomic ions, because this was the molecule that I studied a lot while I was in graduate school. So NO3. So I would put nitrate on the front of the card. And then I would put the formula plus the charge. So NO3 minus is that charge. And there's some, patterns you can see between nitrate and nitrite. So nitrite with an I has a similar charge, but one less oxygen. Sulfate versus sulfite. So sulfate is SO4, 2 minus is sulfate. SO3, 2 minus is sulfite. Okay. So you probably have a table of them that you need to memorize. Okay. So you're not going to be able to skip that. So put them on flashcards, study throughout the day, or index cards. But how do they factor into naming? So remember when I talked about the nomenclature for ionic compounds, they factor in where that anion, for the most part, section goes. They can really factor into either one, because there are like ammonium, NH4 plus, is a cation that can factor into the naming. But remember, when we named our ionic compounds, we would say the cation, and then we would say the anion plus the IDE ending. And then we would put a Roman numeral only if it was a metal or a cation that didn't have a fixed charge. And so the cations themselves, or the polyatomic ions, fit right into this naming system. So let's say, for instance, if we had something like CaNO3 2. Okay. And so I would run through like a series of questions. Well, do I have a metal present? And the answer is yes. I see calcium. Calcium is a group 2 metal. And so I know I have a metal, and I know that it's a fixed metal because it's in group 2. Okay. The second question would then be, okay, well, do I need to worry about saying the charge? Well, no, because it's a fixed metal. So now I would just name this by saying the cation, which was calcium. And then I would follow it up with the anion, which in this case is your polyatomic ion. Now, when you have a polyatomic ion, you're not going to change the ending. You don't need to add the "ide" ending. You just simply put the polyatomic ion. So this would just be calcium nitrate. Okay. Versus if we had something like, let's say we had TiSO4. All right. So if I had TiSO4, I do have a metal present. I have titanium. It's not one of my fixed metals. And so when I name it, I have to put the charge in the name. And the only way I can do that is if I figure out the charge. We can do charge balance still because this entire thing, SO4, all of that is equal to -2. Well, if that's -2, titanium has to be +2 to balance it out. So when I name this would be titanium 2, I put the Roman numerals to say the metal's charged sulfate. Okay. And so you plug them in. The last one I'll do on this real quick is like, what if we had something like, let me clear some space. Because the polyatomic ions I've shown so far have all been anions. But what if you had something like NH4Cl? Well, in this case, you don't have a metal present, but you do have a cation present, right? So this is like I always say your ionic compounds, 99% of the time, they're going to have a metal. They will have a metal. This is the 1%. You don't have a metal, but you do have a cation, a positive cation, which is ammonium. Ammonium NH4 plus is fixed. The charge of it is fixed. And so we wouldn't need to state its charge when we're naming it. We would just now say ammonium chloride. Okay. So I hope that helped, Deborah, with your polyatomic ions, so that we can you can get some naming done correctly. I did see a question about freezing point and boiling point depression from Purvi on TikTok. I don't think I have time to do a full problem, but I do just want to talk about what's happening there. Okay. So freezing point depression and boiling point, it should be boiling point elevation, happens when we're adding a solute to a pure solvent and we're changing the boiling point or freezing point of that substance. Okay. We actually do this all the time. For anybody that lives in a cold state where you get a lot of snow outside, what do we do outside? Well, when we know snow is coming, we put salt down, right? And that salt is put there because it becomes a solute that can now create a solution with the water or the snow or the, that's present. By adding that solute, it's going to cause the normal freezing point of water, which we know should be 0 degrees or 0 degrees Celsius or 32 degrees Fahrenheit. By adding that salt, it actually makes the freezing point of the solution lower. It depresses it. And the more salt we put down, the lower it's going to get to. And so it prevents it from freezing. My niece actually asked me a question about this recently, like, why do we put salt down? Well, that's why, because it's lowering the temperature that water solution is going to freeze at. Same thing with boiling, but it goes the other way. With boiling point elevation, when we add a solute to the solvent to make this new solution, it's going to cause the typical boiling point to elevate. So sometimes you might have seen this where people put salt in their water when they're boiling pasta, and it's like, oh, so the pasta doesn't stick. Yeah, and it's going to make the boiling point of water, which is normally 100 degrees Celsius or 212 degrees Fahrenheit, go higher. Okay. And so in both cases, when you're doing freezing point depression or boiling point elevation, you have to know how much of the solute you're adding, and then you'll do a calculation adjustment. I'll make a video about this one on my channel because I know we're just about out of time to help you out, Purvi on TikTok. And one last question, I saw something that I wanted to try to touch on. Formal charges, Deanna, I will also try to get some videos made about formal charges for you as well, because we are just out of time. I can't believe how fast time went, y'all. I hope you all enjoyed this session. Please be sure, feel free to come back next week. We'll be here at the same time, same place, 8:30 p.m. Eastern, 5:30 p.m. Pacific time. If you want to see more resources that Chegg offers, you can scan that QR code that's in the top corner and check them out. But I had fun going over these problems with y'all. Again, I'll make some additional videos about formal charges and about freezing point depression to try to answer some questions. And I see precipitation reactions as well. So I will get to y'all, and I'll definitely be sure to start with some of those topics next week. But hope y'all enjoyed it. Good luck on any homework, tests, quizzes that y'all have coming up this week, and I will